this problem again is asking you to calculate the velocity for a spring mass system, which requires the understanding of conservation of energy. In this case, the mechanical energy or the kinetic energy is changing into the elastic potential energy. Okay, so you have a spring mass here. Let me draw this one more time. So you have one mass here, and then you have a spring here. Okay. This is spring here, and this block is moving at 5 meter per second. As it's saying, 5 meter per second. What happens? And the mass is 5 kilogram. The mass is 5 kilogram. When this block hits the spring is compressed. Okay, so this kinetic energy is changing into the potential energy. So, okay, now let's see. So the maximum it has compressed when this block is moving, the maximum it can compress is 0.68 meter. That means that this distance is points. So this is the maximum compression. I call this displacement as x2, which is equal to 0.68 meter. 0.68 meter. That this distance. Okay. And then it is asking you what is the speed of the block when it has moved so that a spring is compressed by only 1/2 of the distance. So it is asking you at this point what should be the velocity when this compression is only 1/2. So let's say this is x1. So you need to find out the velocity at this point. So once you have this block approaching towards the spring, then it just tries to compress the spring, and the maximum it can compress is 0.68 meter. What should be the velocity when the spring has compressed only half of this one? So half of this one is so this one x1 would be x2 divided by 2. So this one would be 0.34 meter. So once the compression is only 0.34 meter, what is the velocity of this object? So just going to use the conservation of energy. Okay, I'm using this side here. Okay, so let's start with the at this point. At this point, the potential energy, all the kinetic energy is stored in the form of potential energy. When the spring is pushed back, all the energy, the kinetic energy is now stored in the form of elastic potential energy. Let's say this point is B and this point is A. So at point B, the elastic potential energy, this is elastic potential energy, is equal to kinetic energy. Okay, this is the elastic potential energy. This has to be equal to the kinetic energy. And if you remember, this elastic potential energy is equal to half K x2 square, simply because I'm using x2 here. And what is the kinetic energy? Half m v square. This velocity is at this point. This velocity is v here, and the velocity at this point is 0. This velocity is 0 here. Why is that? Because all the energy has been stored in the form of potential energy, but at this point there is certain velocity. We call that as a v1. Okay, now this half cancels out. I'm just finding out k2 here. K, the spring constant, m v squared over x 2 square. What is the mass? The mass is 5 kilogram. The velocity is 5 meter. So this is 5 square, and this distance is 0.68. 68 square. And if you do your math, the answer for the spring constant, this we just calculated the spring constant now. This gives me the information about the spring now. Okay, we got this one now. And now let's move back at the point A. At point A. At point A. What's happening at the point A? You see, the total energy has to be the same. So at point A, the kinetic energy, I'm just calling this point, let's say, call A, B. I'm just putting this name here as, let's say we call this as a C. This point we call this point C. This is point A here, and we're calling this point C here. At point A, the kinetic energy at point C, this is equal to, it has to have two forms. Kinetic energy at point A, B, kinetic energy at this point, A, plus the elastic potential energy at A, because it does have both energy there. Remember, all the kinetic energy at point C is equal to the kinetic energy at point A plus the elastic potential energy at this point, A point. So that's all I'm doing here. Okay, so what is the kinetic energy at point C? Half m v square vc square, and kinetic energy at point A is equal to half m v a square plus elastic potential energy is equal to half k x1 square. Okay, we need to find out the velocity v here. Half is cancelled out, so m v a square is equal to k x1 square minus m v c squared divided by m, and then this will be the square root. Okay, so I'm just solving for VA now. What is the spring constant? 270. What is the distance x1? X1 you see is 0.34 meter. I think I need to change one thing here. I think this has to be negative and this is positive, because when you take this side, VA, we're just solving for this VA, so this has to be negative here, and this is positive. So this is negative 270, and the x1 is 0.34. That was just a typo. The mass is again 5 kilogram, and the velocity is 5 squared, and the mass is again 5. Just solve this one, this equation, and you will get the 4.3 meter per second. This is the velocity at point A.